So for our next example, I wanted to look at this interesting equation, and we're going to try to think about what sort of surface it graphs. And so what I want you to notice is that I have x squared terms, y squared term, and a z squared term all present. Let's write this down. So you can see that x squared, y squared, and z squared are all present, and they're all positive. And so you know that this thing, this graph, is going to be an ellipsoid. It might be a bona fide sphere. I don't know. But when I put it in standard form, I'll be able to tell. And so I'll just simply say you need to complete the square in each variable to put in standard form. And I'm actually not going to do that with you. So I did it in the last example, and you can practice this one if you want to. All right, so the big point here is you can tell this is an ellipsoid without graphing it because you have each of those terms are present and they're all positive. That's the takeaway. Now, if they were all negative, you could move them all across the equal sign to the other side and they would all be positive, and so that would also be an ellipsoid. So be careful with the negative positive thing. All right, well, let's go on to another example, and we'll work this one out as well. So this is kind of a general case here. We see that I have x squared, y squared, and z squared. They're all present, but now I've got, first off, equal to 1, and I also have one of them is negative. And so that's really the situation here. So I have x squared, y squared, z squared, all present. And I have everything equal to 1, and I have exactly one of these, the z squared term, is negative. And so in this case, you know something. This is always going to be a hyperboloid. What an awesome word. You should enjoy saying it a few times. Hyperboloid of one sheet. And the fact that I'm sort of specifying that there's one sheet should make you wonder, are there hyperboloids of two sheets? And the answer is, well, you'll have to wait and see. All right, so let's do a couple of traces and try and figure out what on earth is going on here. So let's just say traces. And so let's start with the z traces. So I'm going to just set z equal to 0. And when I do, I get an old friend. I get x squared plus y squared equals 1. This is just the unit circle. Interesting. So when you slice this thing horizontal, z equals 0, you get a circle. And okay, what if I do like z equals 2? Then I get x squared plus y squared equals 5. And so I just get a bigger circle. And now we realize that's supposed to be a circle. Now we, whoa, let's make it bigger. Okay, there we go. Now we realize that any z that you pick, when you fix z, it starts out negative, but then you bring it across and it's positive. So you're always going to have x squared plus y squared equals to some positive number. It's always going to be a circle. Any slice that's horizontal is going to give you a circle. Okay, so we've got those traces figured out. They're sort of different size circles. They're smaller. They're like down to the unit circle. Here, let's actually kind of sketch a picture. So down to the unit circle, and then bigger, and then bigger, and then bigger. And if you go negative, it's the same thing. They get bigger and bigger and bigger. So we can kind of get some sense that the picture, the surface should look like that. That's actually what it looks like. But let's do a couple of the other traces as well, just to see what's going on. So what if we fix y equals 0? When I do that, I get x squared minus z squared equals 1. So x squared minus z squared is 1. Hopefully you recognize this is a hyperbola, and you stretch this thing along whatever variable is positive. X squared is positive, so when you sketch a graph of this, you can spend a lot of time with the details of the hyperbolas. I don't need the details. I just need basic sketches here. So this thing is going to open up following the y-axis, and it's going to look something like that. So that's when y is 0. By the way, that fits the rough graph we just sketched a minute ago. And then if you want to check x equals 0, I don't think I want to work in pink. Let's change that. Let's make it purple. Okay, so when x is 0, whoa, there we go. When x is 0, I get y squared minus z squared equals 1. So exactly the same equation. This one was in the xz plane, and now I'm going to get an equation in the yz plane, and I usually let z be the vertical axis. And so it's actually the exact same graph. It's just different labels on the axes. So this ought to be enough now for us to put this thing together and try and graph it. So here we go. Let's do it. So we're going to have this one, and then this one. We're looking at this from the x, y, z perspective. And so now we'll try. Let's do, I don't know, let's do this color. So we said when z was 0, you get the unit circle. And so I'm going to try to graph that here. Let's see if we can do it. Something like that, not too bad. And then as you go up, the circles get bigger. So the circles get bigger in sort of a systematic kind of way. And then the same thing as you go down, they get bigger as well. And so you sort of, oops, this is hard to graph. You can sort of get a sense of what this looks like. Now I need you to realize that the graph of this thing, the circles aren't really on the graph of this thing. They're just helping, I mean, yeah, okay. They're lying on the surface, but we're seeing through the graph, right? If you think of the graph as transparent, then you can take that, any one of these slices. When you slice z equals 0, you get out this circle, and maybe this is z equals 2, and so on and so forth. But that's my rough picture of a hyperboloid of one sheet. And I think I'd like you to see what it looks like on Mathematica. So let's switch over there now. So there it is. There's this hyperbola. I love how it's hollow in the middle. That's pretty cool. Hyperbola of one sheet. And yeah, pretty cool. So let's look at some of the slices. So first we're slicing this by fixing y. And when you look at that, you can see the hyperbola intersection that you get, which is exactly the traces that you would draw by hand. All right, so this is when you fix a y. And by the way, they change. So on this side, when y is negative, the hyperbolas point up. When you switch over here and y is positive now, the hyperbolas point to the left and to the right, depending on how you do that. Actually, I'm sorry, I said positive and negative. It's not positive and negative. It's actually how big y is. When you're bigger than -1, and then when you're inside absolute value of y less than -1, and then they switch back out again. So there's that switch point. The middle point is when absolute value of y is between 1 and -1. So you can see that. I don't think we picked that up when we did it by hand, but that's okay. Again, when you're doing it by hand, the goal is just to get a rough sense of what it looks like. Here's the graph when you fix x, and so you're going to see that same thing happening. When absolute value of x is outside of 1, then the hyperbolas point up, and then all of a sudden, when the absolute value of x is inside of 1, when you're inside that unit circle, then they point the other way like that, and then all of a sudden they open up again right there. There's like that magic point where they switch. So that's when you fix x and intersect. Here's positive x, and then we can go ahead and fix z. And this is, to me, the most helpful of the slices. Sometimes certain slices, just that particular slice is enough. And so this one, when you realize, oh look, as I slice it with negative z's, as z gets more and more and more negative, I get bigger and bigger and bigger circles, right? We'll bring it up now. And then I hit the unit circle in the middle, and then as z begins to get bigger and bigger again, then I get bigger and bigger and bigger circles. And so to me, that was the one that helped me be able to visualize this in my mind on paper. So that's a hyperboloid of one sheet. And so let's see what we come up with in the next example.